I try to explain what they're actually doing for the last 20 years, basically, the finite dimensional integrable systems. Before that, I did very other things, but in the last 20 years, this is the main focus of my work. So the plan of the lecture would be first lecture, and the first lecture should be some three parts. Generalities, and what kind of systems, what kind of dynamical systems am I dealing with? And the second part would be something like first proof, all kind of first proof. First proof that those systems are integrable in some sense. And then the third part is some kind of second proof. I don't tell you what I did, but this is my plan. It should take 20 minutes or so. But I will not do that in my class. Okay, so since we are in this, and the second lecture, and second lecture about the second double. Now I will tell you what are these doubles which I'm talking about, which is the so-called Heisenberg double. Not sure Heisenberg. Although the name excellently comes to quantum mechanics. And this is the some examples that do the third double. Now, a lot, but I'm sort of not trying to do this in a relatively easygoing way, which is not good for sure. But since I wrote this second double and third double, maybe I first tell you what are these doubles. So first start with the compactly group, and I will assume that this is the simple Lie algebra. Don't say it's a simple Lie because it can have a sentence. It's a compact Lie group with a simple Lie algebra and finite dimensional. And I will assume to avoid some complication that connected and simply connected. And I will denote I cannot write Gothic letters on the blackboard. So I will denote the Lie algebra of this Lie group by this kind of calligraphy. And the first double is simply the cotangent bundle of this Lie group, which we can trivialize it by right trivialization to Lie group times dual of the Lie algebra, the tangent with an identity, and by the killing form, we further identify this as a manifold with manifold. Times. And I often denote the elements of this manifold as Gj. G is from the group, and J is from the Lie algebra. So this is the best example. I will move the first example. First double. For the second double, since I mentioned this double, the second double, to talk about the second double, I need to introduce the complexified, like SLNC, and also complexification of the compact Lie algebra, and I will look at this as a real Lie group. Realification. This is my strange notation. Too many indexes, but anyhow. So then I have a certain submanifold inside this complex group, which is exponential of I times the compact algebra. And this is known to be a diffeomorphism between the algebra and this manifold. And this is a closed subset of this group. And my second double, I will denote this double as M1. This is the first phase space manifold. The second double as a manifold again has several models. I actually use 3 models of this manifold. The first model is just the complexified Lie group as a real this manifold, but a certain way which maybe I will explain in this. I don't need to explain this at the moment. As a manifold, this can be regarded as Cartesian product, and so it in a way is analogous to the cotangent bundle. You replace the Lie algebra by this exponential.
P, you take exponential of the complex Lie algebra, or
the exponential of the compact Lie algebra, I times the compact Lie algebra. So in a way, this is in the simplest case when we are talking about S2N, and this is Hermitian matrices, and this exponential of Hermitian matrices, positive definite Hermitian matrices of determinant form. Okay, and both of these are symplectic manifolds. And this is standard symplectic structure, and here there is also a well-known symplectic structure which comes from the theory of Poisson Lie groups. I don't write this at the moment. And the third double, as a manifold, is just the Cartesian product of this compact itself. This is called the quasi-Hamiltonian, quasi-Poisson double, which has to do with the work of Alexei Malcolm and Meinek, and maybe Alexei, I don't know, perhaps it was mentioned in his talk, possibly. So this is not a symplectic manifold, but it also has two-form, bivector, and interesting structure with which you can do integral systems with that. So these are the 3 doubles I will be dealing with. Okay, so I told you what are the 3 doubles. Okay, so what kind of systems? So maybe, especially since we are at the Schrödinger Institute, let me just to keep things secret. Let's just mention the Coulomb-Kepler problem, the hydrogen atom problem, for which we have the Hamiltonian in classical mechanics, the Hamilton function, this moment is a vector, some positive constant over R in three-dimensional space. And alpha is just the coupling constant, the product of the charge of the electron and the proton with a side. Okay, and in this we learn in elementary studies that when we write the equation of Hamilton's equation, there are several integrals of motion. The one integral of motion is let me write this vector notation, the angular momentum vector. And the other constants of motion has many names. This people call it Laplace, Runge, Lenz, Pauli, whatever vector. It was maybe Laplace who found this first, I don't know. It is given by this formula. So the R equals 0 when it of course excluded. And all of these are constants of motion. Here the phase space is of course just two dots, so origin is removed, to, if you like, the coordinate and the momentum vector. And there is the usual Poisson bracket. So let me just add by the components of the position vector Pj this is delta Ij, and the other fundamental Poisson gets between these variables are 0. So here it turns out that right, is it okay? Right. So if you take the Hamiltonian, the square of the environmental vector and the third component, then these three functions are in involution, in the sense that their pairwise Poisson brackets vanish. And this is an example of a so-called Liouville integrable system. So Liouville integrable system in general, in a symplectic manifold, that you have some Hamiltonian which covers the dynamics and number of constants of motion, and the number of independent modes of motion is half the dimension of the symplectic manifold that they are in involution. This is the integrable system, and if the joint level surfaces of the integrals of motion are compact, then they are generally tori, and the dynamical equation of motion can be solved by quadrature. So, but there's another interesting structure in this Kepler problem, because we have more constants of motion than these three. So apparently you have, it appears that we have seven constants of motion, but this cannot be because the phase space is 6-dimensional. So there are some relation between these constants, these constants of motion, and the relations are that you can see that this dot product, which I don't like, but now I wrote this, so I don't write this in dot product. The inner product of these two vectors is obviously 0, so this is one relation. And the second relation, which I had to calculate during the lunchtime, okay, so you can, of course, it's elementary to calculate that you have that this is alpha squared, n squared plus 2m L squared, the Hamiltonian. So there are these two relations between these seven constants of motion. So in effect, you have 5 independent constants of motion. And this is an example of so-called maximally superintegrable, maximally degenerate system, which means that in a symplectic manifold you have number of constants of motion, and this number is a dimension -1. And actually, I decided just today to mention this in this talk because if we view this as a model of the hydrogen atom, there is an interesting historical fact that actually the first quantum mechanical calculation of the spectrum of the hydrogen atom energy eigenvalues were calculated by Pauli with using this algebra quantum mechanically. But I mean that I did not write the multi-or Poisson between these variables, but you can discover that energy levels, this is for Lie algebra, and with certain relation between the cosimics come from this, and it determine the spectrum. And Pauli did this to publish a paper in a little bit less than 100 years ago, in 1926 it appeared. And at the same year, Schrödinger's paper appeared in the wave matrix. And I don't know whether he solved the hydrogen problem in the same year, but certainly it's a bit late. It appeared later than Pauli's algebraic calculation. So this is okay. So from this example, let me go to the general definition of so in the title of my talk is very long, but degenerate integrable system appears in the talk. I think it's a good construction of degenerate integrable system, Poisson reduction of doubles of compact Lie. So in general, what is a degenerate integrable system? So let me give this definition. There are several sort of more or less equivalent definitions. Now I give my favorite definition. So first, so this degenerate degenerate integrable system. This is the name used by Nekoroshev, who made an influential study of such systems, I think 72, on symplectic manifold. And it's very variant of his definition. So let's first suppose that we have some symplectic manifolds. This is symplectic form, and I write the Poisson, the associated Poisson structure. And suppose we have two points. So I mean, then I'm working in the C infinity category. Your manifold. So this is a Poisson algebra. So now we have in the degenerate integrable system we have two Poisson subalgebras, which everything is somehow becomes letter H here. So, but these are some kind of Gothic letters that I cannot write. So maybe I underline it here because they will functions f. So these are Poisson subalgebras of this. The Poisson algebra smooth functions with the Poisson structure, and this is abelian. So elements the Poisson make it vanish, this age is contained in this F, and the F age is 0 for all H from the H and F from the F. So what I mean is that so the H is the sort of the algebra of Hamiltonians of interest, Hamiltonian functions, and the F is the algebra of constants of motion, or some constants. So every element of this F is the constant of motion for every Hamiltonian H, now we assume that further thing. So, for instance, here the example is what I said is you take all these constants of motion and they generate the F and you can find them. So you can just take a Hamiltonian, just one Hamiltonian. Okay. So what we assume that there are some numbers and also some further conditions. So we talked about the functional dimension of these algebras. So this means that so this is, let me call this R, and the functional dimension of the other algebra functions. This is called S. So this means that the elements of this algebra of functions, you take those functions, you take their external derivative, and you consider the span of their external derivatives at points of the manifold, and they span an r-dimensional subspace or dense open submanifold. And then we say that this algebra's functional dimension R.
Generic points.
Generic, but generic for me means dense open subset. Some people use a measure or dense open subset. So the condition is in the symplectic case. So this R is smaller than 1/2 the dimension of the manifold, and the R plus S is the dimension of the manifold. Anyway, this R can only be at most half. When we have half the dimension of the symplectic manifold, then this is the Liouville integrable system. So this is degenerate integrable system on symplectic manifold. R is smaller than half the dimension. But I will be mostly working with Poisson manifolds, but also symplectic, but Poisson symmetrical. So Poisson manifold, this notion can be generalized in the following manner. We keep all these things, but a little modification. So suppose that now that we continue here. So now we have Poisson manifold, only Poisson structures, and by that. Okay, and let's suppose that 2m. This is smaller or equal, but so 2m is the dimension of generic symplectic leaves. So we suppose that manifold is such that on some dense open subset is filled by symplectic leaves of dimension 2m. Then we have these definitions, defining conditions here, and we suppose that r is smaller than m. And in addition, we assume that let me write it. The span of Hamiltonian vector fields generated of this age is R generically. So this is additional. So all the conditions are enforced, which I said for symplectic manifold. In addition, it is symplectic manifold. It's automatic that the span of the Hamiltonian vector fields of those Hamiltonians are generically because the symplectic manifold. Of course, manifold the functions there could be Casimir functions can have zero Hamiltonian vector field. So basically, this is the algebra of Hamilton function I mentioned, and their Hamilton vector field generate subspace of the tangent space of this dimension generically. So this is used by some people. And I don't mention, but in these cases there is sort of action angle theorem, how we construct action angle coordinates by the Poisson case, especially by Miranda and co-authors, other two authors are more difficult to pronounce the names. Okay, so I said these basic notions. Okay, fine. So what kind of systems I'm dealing with? So because this is still the first point. What kind of system? So the kind of system which I'm really interested in is so-called, or which anyway comes up here, Sutherland, Reisenars, etc. And with external spin variables. So the simplest system is this so-called. I just write the classical Hamiltonian. 1 to n pi squared plus some I smaller than j or smaller than j. Some constant that was method. Minus 2j squared. So this is particles moving in one dimension with coordinate q and momentum p, and this is the so-called Cologero-Moser system. And it's known to be a Liouville integrable system, but this was discovered in 71 with Moser constructed and Glasper for 75, or the Jacobi knew the C particle case in the 19th century. It's not very constantly. So this is Liouville integrable system. But there's very okay. So let's, because I don't have much time, let's not write spin version of this. So the other example, actually, I'm more interested in trigonometric systems in this talk, or in general. But generally, these so-called many particle many particle systems usually come in three generations: rational, trigonometric, hyperbolic, and elliptic. And I'm still mostly at the trigonometric level, or in the last talk there will be something elliptic perhaps also. So the trigonometric version of this is so-called Sutherland system, in which you have a similar. This constant doesn't matter. J maybe. So this is some particles moving on the circle, and this is the distance between them, or twice the distance on the core distance. So this is also a famous Liouville integrable system, and this system has a sort of so-called spin analog. So the simplest spin Sutherland model is the Hamiltonian is this one. Plus, so we have here, I tell you in a second. So why would be this one so no, I have a terrible accident here. Because I have something in my ear and
That's something from now, right?
yes, but anyway, be careful because it's rather expensive. Because I told you that my hearing is not very good, and that actually the first time I'm basically using this device. So, maybe you can come some extra time, can you do that? Okay. Okay, sorry about that. So here, what we have is the Q's and J's are just Q and P are just coordinates. This Q is coordinate on the circle because this exponent of square root minus 1 Q is the actual values in the circle. And here this psi is an element of the algebra of SUN or UN with zero diagonal. So it is some anti-Hermitian matrix with zero diagonal. It is also an dynamical degree of freedom. So the phase space here, the phase space structure is something like torus, regular part times SUN. So what I mean here that of course this particle coordinate cannot coincide. So we have n particles. So basically this Cartesian product of the circle n times it is a torus, the maximal torus of UN or SUN, and the Q and P are coordinates there. And the psi is I said that is SUN matrix, but it can be identified with dual space. And the diagonal is zero, and this matter up to conjugation by the torus. The reduction of the algebra of SUN at zero moment of value by the torus. This is the so-called standard spin-Sutherland model. This is a degenerate integrable system, and there is the algebraic generalization of this. I'm not doing very well with the time. The algebraic generalization is so we have some. We have this complexified Lie algebra, and G0 is, let's suppose that this is maximal abelian subalgebra of the compact Lie algebra. So this complexification is the Cartan subalgebra of the complex Lie algebra, and we have some root system with respect to this Cartan subalgebra, root system. System of roots are called alphas. And we have some. And I want to write a Hamiltonian. And I need, then there will be in this Hamiltonian, there will be some spin degrees of freedom which called psi. And the psi is written like this. This is sum over let's choose some positive roots, some alpha from positive roots, and psi alpha minus psi alpha complex conjugate minus alpha. So here this E alpha, E minus alpha, H alpha. This is a wide Chevalier system of generators of the complex Lie algebra. So it's kind of step operator, root vector minus root vector, and this is standard SL2 generating element. And so this is a spin variable, and the Hamiltonian of this spin-Sutherland model, which I am going to, which I'm interested in, is function of Q, P, and C, and the exponential of IQ is from the regular part of the so I have the compact D group and regular part, and the Hamiltonian would be 1/2 E. So this is the Killing form, the Killing form, and this IP belongs to the maximal abelian subalgebra of the compact. This is kind of kinetic energy. My notation is this. I said that I don't take care of the 1/2, 1/4, and so on. The constant do not really matter here. So it is the sum over positive roots and this psi alpha and this sinus squared alpha q over 2. So this q is also an element of psi times these variables. So this psi really, this variable belongs to the dual space of the compact Lie algebra reduced at the zero moment map value by the maximal torus. And this is an example of so-called spin-Sutherland model. And the degenerate integrability of this model, so this degenerate integrable model, it was basically established by Reshetikhin in here. I think he wrote a paper in 2003, Letters in Mathematical Physics, in which he says that he thanks you for discussions about this system here at the Schrödinger Institute. Okay, so this is the kind of systems I'm interested in. Now, so probably I will not have time to explain the second proof for sure, but I did not say what kind of proof, what sort of things I'm doing. So now let's turn to the second part of this lecture. So among others, I want to explain a kind of proof of degenerate integrability of this system. And by mechanism which works in many other cases. So let's say that this M is this cotangent one. Cotangent one. Okay. And then from the cotangent bundle we have two. This is as a manifold. It is identified like this, and we have sort of two projections, pi1, maybe pi1 and pi2. This goes to G and to the algebra, first and second factor, and let's take the following, that we take I2 star of C infinity the algebra invariant functions. Invariant functions with respect to the adjoint action. So in other words, I'm going to take Hamiltonians, which I said that the variables are the G and J, which depend only on G and the G, the algebra element. And for me, the adjoint action is just denoted by conjugation, as if it was a matrix group. So it's invariant Hamiltonian, and one can show that this is an Abelian subalgebra of the Poisson algebra there, and moreover. You can also, and then there is also on every double there are two such distinguished Abelian Poisson algebras, but I don't have much time to go into that now. So we could as well project into the first factor, and then take the invariant functions on the group and pull them back to the phase space. That will be another Abelian Poisson algebra, and that will eventually give rise to another degenerate integrable system. Okay, but. So in order to talk about so I said what are the Hamiltonians. So I'm doing, I will apply some reductions, some symmetry reduction to this system. So I said what are the sort of the Hamiltonians, interesting Hamiltonians before reduction. I did not tell you yet what is the reduction. So but in order to talk about the constants of motion, the F. So let's write down the solution of Hamiltonian equation associated with such a function. So if we have this function defined on the real with H, then of course we can talk about its sort of extra derivative of gradient. This is we can take it to be real algebra value because we identify the real algebra dual space by the Killing form, by this invariant non-degenerate binary form. And then the integral curve of Hamiltonian, this sort of woman, this Hamiltonian, it is something which cannot be simpler. So this let's call the variable t is the time. So this is exponential of t times d age at j0 as d0 j0. So this is so it is kind of orbit of, so this is one parameter group in our Lie group, and this This is always also geodesic on the group with this initial value, and the J component is constant. So obviously, so this must be an integrable system because you can just write down the solution. So you can observe that by using this. Should I continue this thing? Okay. So I'm going to now introduce a map from my manifold, and this is called field psi, into another manifold, which is. In this case, I'm writing also this because in all the other cases, a similar thing, which I'm now showing on this example. So this is Lie algebra times Lie algebra, and this map is the map of constants of motion, if you like. So to this J element of my phase space, I associate the following, that this is G minus 1, J. And you can see that because it's an invariant function, so because it's invariant function, it is true that this J and J, this is 0. So you can easily check that both components are constants of motion. Okay, and also this is also Poisson map. If this is the cotangent bundle, and I mean this Lie algebra really should be thought of as the dual of the Lie algebra, the Lie Poisson method. So if you like, this is G star, and this is G star minus. So G star, this means that this is the Lie Poisson bracket. I think Professor Laszlo called it plus Lie Poisson bracket, the standard one. But the minus one times is also Poisson bracket. And so this is actually the Lie Poisson bracket here and the minus Lie Poisson bracket there. Then this is the Poisson map. Okay, and
sorry, what is M?
M is my phase space, the cotangent bundle, the Lie group times the Lie algebra. Okay, and now I need some blackboard. Maybe I prefer to use this less advanced device. Okay. So obviously the psi. Now I just write this concrete manifold, G times G. So this is actually you said this, the G equivariant Poisson. Now I introduce action of my group, of the group G. So I'm going to some symmetry reduction. So I have to say what is the symmetry and how I reduce. So that's eta be an element of my compactly. And the action of this eta on the original phase space, Gj, is the action of the group element on the point of the phase space. This is just by sort of conjugation. Of course, as I mentioned here, how this means the adjoint action on the Lie algebra. But in a minute, it's better to use this notation. It seems simpler in many cases. Okay, and also similarly, the action on the tangent space is this is the action on M, and the action on maybe on the n manifold, maybe co-element J twiddle and J. This is similar. This is eta J twiddle eta inverse J eta inverse. And this is the next variant. And this of course because this is basically the cotangent lift of the conjugation action on the group. So this is I don't want to talk about this is generated by moment map, but I don't necessarily for me to talk about that, but maybe mention that the moment map in this game and the moment map is this J minus 1 J. This is the moment that is generates this action through the usual rationality of Hamiltonian mechanics. Okay, so now lattice map side. Now I introduce. So I want to construct some. So my philosophy is that first I write some degenerate integrable system on some group theoretical natural nice free spaces, nice symmetries. In this case, the cotangent moduli. And I write the constants. Okay. This is just a complicated way of writing that. So these are basically the functions which I said before that depend on this J and J twiddle. So this cotangent bundle, the symplectic form, this H and F, this is the degenerate integrable system. Phi, then you can of course on the Hamilton's inference comes from the invariant functions of the Lie algebra. By theorems of invariance, they write some invariant polynomials. So the functional dimension of this age is R, which is the rank of my Lie algebra. Rank of my Lie algebra. And now, okay, yes. Now, functional dimension F is twice the dimension of the group. Here is the same minus R. Now maybe I can easily prove this, but basically. But I'm looking at my watch. So, and to anybody asking me, I can prove this. Okay? The basic thing is that there are these two constants of motion. But these two constants of motion are not independent, because suppose that the Ci is an element of invariant function on the Lie algebra, the invariant polynomial. We know that there are independent basic invariant polynomials. So because of this, you see that the Ci, this G minus 1, J minus Ci, J, this is 0. So this from I from 1 to R. So there are relation between these two invariants, and that cuts down the number of components is twice the dimension of the real, but that cuts down the number of independent invariants by R. I can sort of prove it more exactly, but I don't have time for it. So in this way, or the convincing, so this means that we have a degenerate integrable system on the cotangent bundle. Okay. So now comes the reduction. Okay. Maybe this can be seen in this way. Is it okay? Is it okay? Yes. So basically, I'm doing Poisson reduction. This was in the title of my talk. So essentially, this means that I want to give the invariant functions and the space. The invariant functions, of course, form they close under the Poissons of algebra. So sort of morally speaking, this is the same as functions on the quotient space. And this can be made some sense of also. So basically, I want to say, a second, M over G, this reduced Poisson bracket. Now, what is the reduced Poisson bracket? It's just that I restrict the Poisson bracket to the invariant functions. This is the reduced Poisson structure, and they are viewed as functions on the quotient space, on the space of orbit. And my Hamiltonians are automatically invariant functions. So they go, nevertheless I write them as reduced because I now view them as functions on the quotient space. And now I take the reduction of my constants of motion. This just means this. So so remember that F was I pull back the functions from the algebra times the algebra, which is M. Now instead of that, this was F. So I can talk about the invariant part of this F, which I just pull back the just space here. So I just take the invariant functions originally, and they go down to the quotient space. And basically, one wants to say that this is an integrable system, or for instance, what is Reshetik said in 2003? Basically, he said that, well, this is a degenerate integrable system of generic symplectic leaves of this. Generic symplectic leaves. Now I want to make this a little bit better than so basically I am working along this idea. So what I want to prove is this, or what I can prove. I'm not sure I will be able to prove it here. So let's go to the principal orbit type for the action of my group on the manifold. So this means that the isotropic group is as small as possible. Actually, you can see very easily that the principal isotropic group in this case is just the center of the group G. It's just the center. I can also prove it. Anybody wants, I prove it. But it's easy. So now I will write some kind of nice diagram. This C, which is again supposed to be a multilateral. I call this the image of my manifold. This is some subset of G times G. So okay. So you see, this is the principal. The point is that this is a smooth manifold. This is a smooth manifold because there's only one orbit now. And indeed, I can prove, but I'm not sure. I will attempt to prove when you restrict this construction, which is sort of morally given because you can say well-defined object or is not a smooth manifold, when you restrict all this to this principal orbit type, then indeed it is a degenerate integrable system indeed. And the integrals of motion coming from here. So all these functions are defined in the quotient space. You can restrict them to the principal orbit that is a dense open subset, and it's a smooth manifold. And actually, I denote this image reduced star and F reduced star. And if you like, maybe in mathematics we say that theorem. This is a degenerate integrable system. This is one of the theorems. And
So is it true M mod G is a kind of Weil chamber, and the M lower star mod G is the interior of the Weil chamber, or do I have it
so
wrong?
certainly the Weil chambers and Weil outputs coming here all the time. Yes, yes, it has to be that for definitely. But we have Cartesian product. I am using the Weil chamber in the second proof.
Okay.
Which I am quite happy to. So how I prove this? That this is a degenerate integrable system. First, I talked about regular part of my cotangent. I think I can have time to do this. This is. So I just take the regular part of the real. It means that the isotrope is the maximal torus. And the image of this by map, that's called the restriction of my map. Or this is not just my map. This is some regular. So I mean, this is regular part of this image. So this means just pairs of real and both of them are regular and conjugate to each other. So they are the same orbit. So the point is that this is also a good manifold. This is a good manifold. This is also a good manifold. And now I'm going to talk about something even more, like C star. This is the principal isotropy submanifold in there. So again, the principal isotropy group there is. It turns out that again it's just the center. And now I introduce something which is called M double star. This is the inverse of this C star by my map. So I have the following situation that yes. So this is actually sort of this is Conte star. This is Conte this is psi or that's my resident qualitative psi. So the point is that the group has one isotropy type in C star and W star, which is the baggage. And this map is actually a surjective submerger. So I can So I can complement this diagram in this way. I go to the orbit spaces, and these are just smooth manifold, principal fiber bundle. And in this diagram, every map is a smooth submerger, and every map is a Poisson map. And simply, I actually That's the final motion here. So I will give P1 and P2 these projections. So this is psi maybe psi red. So what is this? Psi red star C infinity C star over G. So I take any function of this manifold, and pull them back to my reduced phase space. And since this is a space of constants of motion, so all these are constants of motion for the reduced dynamics. And simply because it's just taking quotient by free action in the center, so you can call the dimension. What is the dimension of this manifold? The dimension of this manifold is the dimension of this one, which is twice the dimension of the Lie algebra minus R, and then minus the dimension of the Lie algebra. So the functional dimension of this, the functional dimension of this F double star is the dimension of the Lie algebra minus R. My original Hamiltonians, they remain independent after this reduction. Actually, I can show that on this part of the phase space, the Hamiltonian vector fields of those Hamiltonians are independent at every point. And the functional dimension of the Hamiltonians was R, and the dimension of this reduced phase space is the dimension of the group. So in this way, I have shown that okay. So I have shown that this M double star over G, I mean my reduced Poisson that is restricted to this tensor and subset is really and restricted to this, and this F double star. This is degenerate integrable system. Degenerate integrable system on this Poisson manifold. And then I show that actually this I had another algebra here. I can show that the function, I mean the after reduction, the functional dimension coming from these functions also is the same. They are not the same algebra of functions, but the functional dimension is the same. And since these functions are globally smooth over the full quotient space, because I was coming from this comes from the C infinity G times G invariant. So they are everywhere smooth. So after that, in this way, I can show that this also in this that star. That star and this red star. That this is actually an integrable system. So first I show this dense open part, and then it extends to this part. And I have this as a theorem. And I have similar kind of theorem which I will mention tomorrow. That so basically, what is? Can I have five minutes? Otherwise, I'm finished basically.
Yes.
Maybe just 2 more minutes is enough. Three.
Okay, so I mentioned maybe they are still in the blackboard. I don't know. So anyway, I have these three doubles. You remember the one of the. So all the three doubles, I have projection into a nice space, the algebra Lie group, or this space of positive definite. So in one double, there are two degenerate integrable systems. And for all of these, this kind of proof is actually actually, to be honest, I push through this kind of proof for 3 cases, not for all the cases. So this kind of proof works for those doubles, and sort of the which I planned as a second proof of these things, that I can also construct action angle values for all these systems, and this comes in the following manner: that since I'm going in the regular part, so I can represent everything by the interior of the Weilchamber. This is what you asked. And so if I take some function of j, I map the j to some by eta j, I map to the interior of the Weilchamber, and the coordinates of this element expanded in this basis of the Cartan generators with the simple roots. They are going to give action variables. They are going to give action variables. So I can construct, and actually they also descend to torus action on this reduced phase. Actually, and this action on this what I call this m double star over g. This is a free action. And I can also do this in the other cases, where when I have the g times g, then I have to conjugate the y output, and similar. It is actually new. I did publish this the concept of action angle values for these systems. Basically, that's it. So I hope that something was understandable.